Okay. I think I've got it. Okay, that's just a second. Okay, does my voice sound completely bizarre and crazy? Can you hear my voice? It would have been funny if every single one of you nodded or shook your head, no, we cannot hear your voice. Okay, so let's see, how do I do this? Technology, don't fail me now. All right. No! Darn it. It has to do it this way? That's so absurd. Okay. I hope you are all doing well today. So here's what's going on. I'm in the lab. I've got my safety goggles. At the moment, they're protecting my hair, which of all things, I do want to protect that dearly. With that said, it's entirely, wait just a second. It's entirely possible that I will have a difficult time, or there will be a little bit of a delay on me responding to things. The reason for that is I have my telephone that I'm talking into, but I also have my laptop computer because I need to be able to record this so I can sell it on YouTube and TikTok and become a millionaire. Now, with that said, I have my laptop muted because whenever I do not have my laptop muted, here's what it sounds like. Yeah, nobody wants that feedback. So that's something that I'm going to have to deal with, and I'm going to do my best to deal with it. Now, I feel like we're ready for lab. We're going to be moving all around the lab space. First of all, I'd like to give you a quick tour of the area because I've not done that yet. So I've got my tripod right here that I'm going to be walking around with. So first things first. Eye wash station. This little paddle right here, you keep that depressed and lo and behold, water sprays up. Water will spray up, I think at about 30 gallons per minute. I think that's about right. Or maybe it's 10 gallons per minute. Either way, it's a huge amount of water. You know what's very important to have near a water source? A drain. So we've got that drain, we've got that water supply. In the event that something happens and you are in an area where you splash water in your eyes or something, this is your best friend. Next up is similarly safe is the safety shower. Safety shower has this handle right here. You pull that down, it stays down. Again, you're getting water splashed or distributed downward at a, I don't know, I think it's about 10 or 30 gallons per minute. So a high rate, a lot of water spills out. Okay. In addition to that in the lab, we've got fume hoods all over the place. If you'll notice, I do not have a mask on because, wait. So no one else is within space of me. So I'm keeping myself safe, keeping other people safe. Now with that said, I'd like to go ahead and get into a discussion of what this week's experiment is consisting of. Now, we are going to be measuring kinetics of a reaction. The reaction that we're measuring the kinetics of is the breakdown of our dye F, D, and C. And we are measuring the breakdown or the rate of that breakdown with respect to a standard bleach solution. Now, I'd like to walk you through essentially the day. We have basically three parts. The first part is, and there you get to see my handwriting. The first part consists of making solutions and subsequently making dilutions. So solutions and dilutions. And the purpose for that is to determine our lambda max. So what wavelength is our compound going to absorb light at? Next up, what we're going to do with that, we're going to make our solutions and subsequently dilutions, and we're going to have to do some calculations for concentration of our solution. Now, what we're going to have to do is we are going to need a total of 6 cuvettes. Now, I'll show you the cuvettes in just a moment, and I'll show you the solutions that we're working with. Once we have all of those solutions prepared and those appropriate dilutions made, we'll be plotting data. So this is something that in the Kinetics experiment 1, or Kinetics data 1 video that I posted. That shows how to do that. That shows how to plot your data to determine basically a good wavelength to use. Next up is going to be plotting data and identifying the dilution that we want to use for our subsequent trials. Now, our future trials are going to be measuring the absorbance that gives us closest to 0.9 to 1. Now, does anyone have, and go ahead and type it into the chat, does anyone have an idea of why we would want to use an absorbance or use a solution that gives us an absorbance close to 0.9 to 1 within that range? Okay, so the thought process is we want to see a solution and we want to see a specific concentration for all of our experimental trials where we're starting at effectively 100%. So if we select a concentration, so I'm gonna write this right here after I get an eraser. That gives a 1.0. So our concentration that gives us an absorbance of 1.0, this is a good starting point because what we are watching is we will be watching the breakdown of the FD and C. So if we start with 1, or if we start with effectively 100%, and after 10 seconds, for example, our absorbance goes from, let me write this out a little differently. So time versus absorbance. If at time 0 and then at time 10 seconds, we see an absorbance go from 1.0 to 0. Let's say 0.83. And then at 20 seconds, you see it go to 0.65. Do you have an idea, or could you look at that and say something about the rate of breakdown in terms of, simply putting it in terms of the percentage that we started with compared to the percentage that we are at a given time. So at this point, we'd be able to say 100% of our compound, of our FD&C, was present. At our last data point, that 22nd time point, you'd be able to say 65% is remaining. And so you'd be able to say something like, well, 35% has been used. Does that make sense? So that's really our intent for figuring out a concentration where our absorbance is 1.0. And we want to start with a good benchmark. Now, the range was 0.9 to 1.0. So it doesn't have to be absolutely 1.00 or anything like that, but you want the best concentration to get you there. Now, does that make sense? Does anyone have any questions about that I should ask? Okay, great. So I'm putting my goggles on, and now I'm gonna get some glovies on. The things that you would be, well, I'll just carry the tripod. The things that you would be working with are a number of different solutions. So the first solution that you'd be working with is this right here. This is our FD&C blue working stock. Mr. Burnett emailed you a file that told you about the concentration of this. And for what we're doing right now, it's not the most important thing, but it's important that you're able to work with calculations where you start with a concentration, or that you know the concentration, because you will later be making dilutions. Now, this piece of glassware, has anyone seen one of these pieces of glassware before? This is a specialized piece of glassware known as a volumetric flask. And what's important about a volumetric flask, and what you'll always notice about one, is that they have a flat bottom to them so they can rest on a table. But then the most important part of them is on the neck, they have this small kind of, I guess, frosted edge or frosted line. Can anyone see that line? Okay, awesome. Thank you for the awesome emojis. Perfect. And real hands. This is great. So a volumetric flask is a good piece of glassware, but it's also kind of an awful piece of glassware. What I mean by that is it does one thing and it does one thing very well. So that makes it good, but what makes it bad is it only does one thing despite doing that one thing very well. This is a 100 milliliter volumetric flask. This is perfect for getting 100 milliliters of a solution. This is awful for getting 99 milliliters of the solution or 101 milliliters of the solution, because that line is your only marcation or your only demarcation with respect to a volume. Now, similar to a volumetric flask, I could totally be an Instagram influencer. I could get used to this. Just walk around with a camera. This right here is a volumetric pipette. Now, a volumetric pipette has the exact same thing. It has a small marking to indicate a specific volume. Now, with a volumetric pipette, what you will commonly see is a bulb or there are some things that are, they're generally, here we go. They serve the same purpose. They work as a suction, but you'll see something like this you can put on the end. And then this has a little wheel that you roll up, and that produces a vacuum that pulls the solution into this bulb and pulls the solution to that line right there. This is a 10 milliliter volumetric pipette. This is perfect for getting exactly 10 milliliters. Now, what I'm going to do today is save us all a little bit of pain and mental anguish and frustration, and I'll save myself from breaking a bunch of broken glass. But if you were in the lab and you broke glass, where would you put it? That's right. The broken glass box. Broken glass box. There's a sign for it and everything. By the sink, there's one. There's one. There's a nice little broom that you could sweep things up with. This is perfect for where you would put broken glass. But I'm going to avoid doing that. One, because I don't like breaking glass, and two, because those volumetric pipettes and volumetric flasks, like I said, they're great for doing one thing, but they're very specialized. And like a specialized surgeon or something like that, there's a premium that comes with their services and everything. So those specialized pieces of glassware are very expensive. Now, with that said, I don't want anyone who's thinking about becoming a surgeon thinking, oh, this is great. This guy I've met 3 times, or now 3 times, has equated my dream profession of some sort of surgeon to a piece of glassware. That's not what I'm doing at all. I'm just saying it's specialized, so it's expensive. Okay, so the first part of your procedure, before I proceed, show of hands, show of fingers on a scale of 1 to 10, how perfectly is this going? All right. Well, the people who have decided to only put the first letter of their name up, minus 1,000. Minus 1,000. Because they did not show 10 fingers. Okay, I digress. I'm not grading based on that. Okay, so the first part of our procedure was to determine the lambda max. So what's the wavelength that is going to absorb our compound and give us the highest absorbance value? So what that consisted of, and I'm going to try to roll this cart that has like 15 laptops in it. Okay. Oh, there we go. It swivels. Right. This is really fun because I'm getting to move around several $1,000s of things and run the risk of dropping them all. Okay, but some of them are mine. Not to say that I have thousands of dollars of things, but you know, laptop and phone and stuff. Okay, so this stock solution is the one that Mr. Burnett referenced and let you guys know about the concentration of it. Now, if you look on page 3 of your procedure, what it tells you to do is make a series of solutions. Now, those solutions are coming from basically that working stock and then being diluted, all using volumetric glassware, volumetric pipettes, and volumetric flasks. The reason for that is accuracy. If you can fill it to exactly that line, boom, you got 100 milliliters. Now, with that said, there is, okay, so now here's the involvement of everyone else part of the class. I'm going to mute my computer, or unmute my computer, and if you hold, okay, here we go. So see this volumetric glass? You see that little lip down there? See how the water kind of goes down and comes back up? Did everyone see that? When you fill a piece of glassware, how there's like a little thing to it. I want everyone to, on 3, say the word for that curve of the solution. On 3.
Meniscus.
Meniscus! Okay, now, the other thing that everyone takes away from certain classes, what's the powerhouse of the cell? On 3.
Mitochondria.
Mitochondria! Okay, excellent. Thank you guys for playing. Okay, So what we will do, and what I did for this was I took, and because the TA who actually prepared these solutions isn't here, I'm going to take complete credit for doing all of her work. So I did all of this. I prepared this solution, and from this solution, I made this solution. This solution has 25 milliliters of FD&C blue dye, and I adjusted the volume to 100 milliliters. So 25 to 100 means that I have approximately 75 milliliters of water. Now, with that said, is this a really good approximate measurement, or is it a really bad one? Thumbs up for good. I'm going to vote for good because of the fact that we're using all that volumetric glassware. I like that I can talk very close to my phone and show all of these solutions. Okay? So the next solution, 20 milliliters of FD&C, 80 milliliters of water. 100 milliliters of, or 10 milliliters of FD&C, 90 milliliters of water. 4 milliliters of FD&C, 96 milliliters of water. 2 milliliters of FD&C and 98 milliliters of water. 1 milliliter of FD&C and 99 milliliters of water. One thing that I need to point out about this is if you look at your data sheet, what your data sheet shows you is all of those solutions that I just described with one that was a little bit inaccurate. So all of those solutions that I just described are accurate descriptions of those solutions. If you look at your data table, what you'll see is solution A, B, C, D, E, and F. And if you look at solution E, that is 1 milliliter of FD&C and 99 milliliters of water. And then solution F is 2 milliliters from solution E plus 98 milliliters of water. What I did was I went ahead and I kept the 2 milliliters. So I made all of these solutions, but I did them a little bit differently. So my solution E is actually 2 milliliters of FD&C and 98 milliliters of water. My solution F is 1 milliliter of FD&C and 99 milliliters of water. And then I have a solution G for the 2 to 100. Does that make sense? Or 2 to 100. So I made all of these, but I made one extra. Makes sense? And the reason, so let me explain this solution F, the way it, and I'm just going to talk about solution F as it's described here. Solution F is effectively to show you a very, very dilute solution. Because let's think about this. And think about it in terms of C1V1 equals C2V2, or M1V1 equals M2V2. I personally am accustomed to C1V1 equals C2V2, but I will stick with M1V1 equals M2V2. So we have our solution E and solution F. We have in solution E 1 milliliter of FD&C, 99 milliliters of water. And then in solution F, we have 2 milliliters from solution F and 98 milliliters of water. So when you're thinking about how dilute solution F is compared to solution E, solution F is 50 times more dilute than solution E. Does that make sense? So your absorbance on that should be super low. And I can tell you from acquiring this data, it was indeed super low. Okay, so I have all of those solutions, and what I did with those solutions was I put gloves on. Glove. glove, or as my oldest son calls them, glovey gloves. With those gloves, I got a cuvette. This cuvette has 2 frosted sides and then 2 clear sides. If you look through, there's the clear sides that my camera is looking through. Frosted sides, clear frosted sides. You want to send your light through the clear sides. And if you're ever like, oh, I can't remember, is it the frosted or the clear sides? What's great about these cuvettes is they have a very small, in focus, I'm looking, they have a very small triangle. And that triangle, what you're supposed to do with it is you're supposed to line it up with a triangle on the light source that you're using. Okay. So what we're using is an instrument known as a spectrophotometer, or if you're cool, you call it a spec, because you don't have time to waste saying words like photometer. You can just say, I'm gonna go use the spec. And everyone's like, yeah, totally, I know. This right here is a UV Vis Spectrophotometer. If you look in there, there's a little hole there that's where you're going to put your cuvette. Can everyone see, in a show of either real thumbs up or emoji thumbs up, can everyone see the triangle? Awesome. So I will line up the triangle on my cuvette with the triangle that's on that spectrophotometer. What you also should have seen was a little, what looked like a sun, that was indicating that's where your light source is coming from. Okay, now, I've done all that. What I did was each one of these cuvettes holds approximately 3 milliliters of a solution. So what I did, okay, we do have a limited time frame because my phone's probably going to run out of battery, but I think we'll be all right. Okay, so each of these cuvettes can hold 3 milliliters of a solution. And so what I did and we're still working on part 1, was I took 3 milliliters of each one of my solutions and I put it into a cuvette. So this right here is my cuvette for the 25 to 100. This is my cuvette for the 20 to 100. This is my 10 to 100 solution. There's my cuvette for that. 4, 4, 2, 2, 1, 1. And then this one at the end here was my extremely dilute last solution. Okay, so I've got all of those. And what I did was I went to my computer and I said, computer, I need you to help me out here. My computer said, I think I can do that for you. Just a second. There we go. Oh, wait. There we go. I said, Macintosh, on. And it listened. And then what I did was I said, I need to calibrate you. I need to make sure that my spectrophotometer is ready to read the absorbance of different solutions. And so what I did was I got a single cuvette and I filled it with 3 milliliters of deionized water. Because deionized water is going to serve as my so-called blank. So here's my cuvette with 3 milliliters of deionized water. Because basically, the spectrophotometer says, I know what water is. I'm cool with water. So that's going to be my benchmark. And I was like, sounds great. So what I did was I said, experiment, calibrate, spectrophotometer 1. I'm going to skip the warm-up because this machine is ready. I'm going to finish my calibration. I placed my blank cuvette in there, and it's going to do some math stuff, make sure to detect some light. I'm going to click OK. Then what I'm going to do is I'm going to jump over here. Absorbance versus wavelength. And I need to switch this to absorbance versus wavelength. Do I want to store the latest run? No, I don't. Uh-oh. We're back. Okay, this is one of the downsides of using your phone as a camera when you get a call. So it was somebody calling, I'm sure, about my vehicle's my vehicle's, whatchamacallit, extended warranty. Okay, so what I want to do is I want to go ahead and look at this and say the full spectrum. I want to look at all of the wavelengths of light. So what I did was I pressed play. So that means I'm shooting light of all of these wavelengths at my sample. And this is my water. So what you're looking for is any sort of peak. Does anyone see any sort of peak on the left, not on the left-hand side, but instead in that visible spectrum? So that rainbow spectrum. Does anyone see a peak? I'm seeing a no, you're right, you don't. I'm not sorry for telling you what you can see and can't see, but no, there's not one there. Next up, I'm gonna go ahead and get my most concentrated solution. Is everyone ready? All right. Booyah! Look at that. That's going up. Can everyone see that peak between the transition from yellow to red? Perfect. So what that's telling us is approximately a wavelength, or our highest wavelength there. Now, what you can do is on the left-hand side of the screen here, oh man, I didn't think about this part. But on the left-hand side of the screen here, yes, sorry. On the left-hand, nope, I can move this closer. On the left-hand side of the screen, you can see a wavelength. And what I can do is I can scroll through those wavelengths and find the one that gives me the highest absorbance. And absorbance is a unitless number. So what I'm gonna do is I'm gonna go ahead and click here. Nope, not there. Click there. And as you can see, hopefully, maybe, I'm not sure, but my green numbers are getting a little bit larger. So just a second. The point is of all this, that the wavelength that we get, our highest wavelength is approximately 632 nanometers. So now I'm going to show you guys the, So let's see. That line right there. Now watch as I replace this solution with a more dilute solution. Is everyone looking in that orange-ish area? Okay, keep watching, keep watching. Oh, the peak is significantly shorter. And that significantly shorter peak is an indicator of there being less of a solution that can absorb light of that specific wavelength. So what I just did with those was I looked at how does my absorbance change based on a solution that is 25 milliliters FD&C plus 75 milliliters of water compared to a solution that's 4 milliliters of FD&C and 96 milliliters of water. So as you can see, when there is less FD&C, you have a lower absorbance. Does that make sense? And through all of those trials, what I found was that 632 nanometers was the wavelength that was the wavelength where my solution absorbed light. Does that make sense? So 632 nanometers was what I got from this, and I can say, boy, howdy, I can move forward with my life. In addition to that, what I found was that my second solution, my 20 milliliters out of 100 milliliters, so 20 milliliters of FD&C, 80 milliliters of water, that was my solution that gave me my absorbance of approximately 1. So basically from part one, so from prepping all of this, I gathered two factoids. The first of which was my Lambda Max, 632 nanometers. The next one was, which concentration do I need to move forward with? How's everyone feel about all of that? Awesome. Okay, so the next part of this is a little bit tricky. And I say that it's tricky because of the fact that what you're going to do is you're going to make a mixture of different solutions, and then you're going to read the absorbance of those different solutions. Those different solutions, I'm going to take you over, I'm going to take everybody on a walk. Wait. Whoa, 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 whoa. Oh no. I'm back. What our cuvettes are going to hold are three different substances. So we have our dilution, we have our solution that we need, and now what we need to do is make a 3x solution. Oh wait. Yes, the peak is at the same wavelength. I'm sorry if I blew past that. Okay. So we need to make a 3x solution. So if the solution that we just used and identified as being capable of getting us to our perfect wavelength, with our absorbance being 1 or 0.9 to 1, does anyone know why we want to make a 3x solution? Before you answer, let me show you what our individual experimental runs are going to look like. Our experimental trials are going to consist of NaOCl, also known as sodium hypochlorite, DH2O, also known as deionized water, FD&C, also known as the solution that we're keeping constant. Now, if you look at these, I have X milliliters of NaOCl. I have Y milliliters of DH2O, and I have 1 milliliter of FD&C. Now, does that give anyone an idea or a clue as to why we need a 3x concentration solution? Well, that's right. The reason is because we're effectively diluting our solution 1 to 3. Does that make sense? Okay. It does seem a little bit odd because of the fact that, well, you just used 3 milliliters, but that 3 milliliters happens to be the volume that we put into our cuvette. And now, what that means is we have to take, or we have to make another solution for all of our individual trials. So if this solution 20 to 100 was the one that we found gave us the concentration that we needed, what we need to do, and what I did, was I took this FD&C working stock and I added what volume of FD&C to what volume of water. And you can type it in the chat if you'd like. I needed it to be a 3x solution. The last one was 20 to 100. So what's 3x concentration of that? Booyah! Perfect. 60 out of 100. So we had to get 60 milliliters of our stock solution and add to that 40 milliliters of deionized water. Does that make sense? Fantastic. So, and this is a little bit confusing, and I hope that I can clarify, or I hope that it's not confusing for anyone. But this right here, this 1 milliliter of FD&C, this FD&C is actually 60 out of 100. But, uh-oh, what's happening to me? Oh, low battery notification. Oh boy. So this is a 60 out of 100 solution, but we're only using 1 milliliter in this full 3 ml solution. Cool? Okay, excellent. Just a second, just a second. Okay, sorry about that. Now we're on to part two. The very first part of part two is, well, determine our concentration. We've done that. We're ready to move on with our lives. We made our 3x solution. Now that 3x solution, just a second, as I move everything out of the way. One thing that I'm going to do is get a test tube and just put some deionized water in that. The reason is because I'm going to have to be using this test tube and this deionized water. Okay, so I'm actually now ready to do some of my experimental trials. If you look at the bottom of page 4, I guess that would be, what you'll find is a table that shows you several different trials. Trial 1, 2, 3, 4, and cleverly titled trial number 5. In all of those trials, one thing that we are going to do is we are going to keep our concentration of our dye constant. So since our volume is a total of 3 milliliters, what we can do to keep our dye concentration constant is keep our dye volume constant. What we're going to vary is we are going to vary our sodium hypochlorite or our bleach solution. That bleach solution, what we're going to do is we're going to start out with varying amounts of bleach. The first trial is going to be 0.5 milliliter or 0.5 milliliters of bleach. The next trial is going to be 1 milliliter of bleach. The next trial is going to be 1.5 milliliters of bleach. Now, in order to maintain our total volume of 3 milliliters, what we'll have to do is we will have to include and adjust our water volume. So when we're doing this, though, what we need to keep track of and remain aware of is the sequence in which we're adding our different reactants to our cuvette. The reason for that is, what is this going to do whenever it comes into contact, or it comes into contact with bleach? Is it going to be like super happy, or is it going to become oxidized or break down a little bit? It's going to disappear. Perfect. Thank you very much, Eve. Wonderful. It's going to begin breaking down. So we would see our absorbance go down. So what that means is if you add your dye and your bleach, and you're like, oh, this is great, now I just need to add my water, and then throw it in my spectrophotometer, or wait, no, we know the lingo now. I'm gonna throw it in the spec. My question is, would you miss a portion of your reaction? Thumbs up or thumbs down? Yes, you would, absolutely. I'm happy that everyone was right in line with me, because I didn't actually clarify what thumbs up meant and thumbs down meant, but everyone, we're on the same wavelength here. We've got it, we're working, awesome. Okay, so as soon as that FD&C comes in contact with bleach, it's gonna be breaking down. So what we wanna do is we want to get a cuvette. Into that, we want to add water and then bleach. Arguably, you could add bleach, then water. The sequence of those two doesn't really matter, but when we add them, we're then going to add, very last, our FD&C solution. And with that FD&C solution, as soon as it's added, we're gonna put our finger on the top of it, yoink, do one inversion, and then very quickly put it in the spectrophotometer. Now, with that said, I would caution you, this is, I don't know if anyone's familiar with or knows anyone who is an EMT or a healthcare professional of any sorts. I'm thinking of EMTs just because they're generally in the high pressure situations where something acute has happened. If you ever, and I hope that you don't have to ever, I mean no disrespect to EMTs, but I hope you never have to be around an EMT. That sounds worse than I wanted it to. But you know, just for safety's purpose. But in the event that you are, just imagine, do you think that an EMT is going to come in and say, hey, how's it going? Well, they're probably not going to say, hey, how's it going? They're probably going to say like, hi, my name is George. I'm an EMT with Austin Travis County. I'm here to help you out. Looks like somebody has a broken arm. Is that what happened? That's option A. Now, option B is, what happened? What happened? What happened? I can help. I'm a helper. I'm a helper. I'm a helper. Okay, so with option 1 being 1 finger up, option 2 being 2 finger, option B being 2 fingers up, let's go ahead and participate. Are we going A or B? Okay, seeing lots of A. Okay, good. Oh, Eve, why'd you do that? Okay, Eve, in the event that you ever meet an EMT who does that and is like, I can help, say, do you have any other people who can help out? Maybe you should just do a ride along and hang out for this one. I appreciate it, but I am now more calm than you are. So I don't know, just pump the brakes a little bit. Okay, so the reason for that, and the reason that I bring that up, is because this is time sensitive, but you want to be accurate more than you want to be finished with it quickly. So what I mean by that is you should say, all right, I've added my first water and my bleach. Now I'm going to add my FD&C, cover, invert, done. Okay, so no frantic hands flailing or anything like that. Now, with all of that said, one thing to keep in mind is, since this is time sensitive, you're using the spec to shoot light at it, you want to start recording the wavelength, or you want to start recording the absorbance prior to actually inverting and putting it in there. You don't want to invert, put it in the spec, and then press record and observe that time. Deal? Yeah, awesome. Okay, so what I'm going to do is we're going to do 3 trials, and then we're going to talk about how we can move forward with that, which if I time that properly, then my phone will be at 5%, and we'll be able to complete this aspect of the lab, and then I'll just switch to this one. With that said, I got an iPhone a couple weeks ago, and I only have like one of those cords because my wife has Samsung phones, and I can never find my iPhone port, and I always just try to plug the Samsung ports into it. Because it's an iPhone 7, it's refurbished because it's cheaper that way. Wait, it's refurbished because it's cheaper that way. Also, Boost Mobile is cheap. Anyway, it is. You don't get service in parts of the United States, but, you know, just, I don't know. Okay, so here we go. Pipetteman. This one, I have a little locking mechanism right here. I'm going to lock that because I've already got it set to 1,000 microliters. 1,000 microliters is equal to 1 milliliter. What I'm going to do is the very first trial I'm going to do is going to be a mixture of 1 milliliter of bleach, 1 milliliter of water, and 1 milliliter of my FD&C, okay? Now the first thing that I want to do is, and you'll have to look at the other version of me for a second. Oh, computer fell asleep. I'm going to go, it's a spinning rainbow wheel, so no apples. It's going to wake up in about a year. Ugh. Just kidding, just a second though. Okay, here we go. I know my wavelength, and I know that I'm talking to not my microphone, but here I am. I know the wavelength that I need to use. That wavelength is 632 nanometers. So what I'm going to do is I'm going to come over here, and I'm going to configure my spectrometer. The graph that I'm going to use for my spectrometer is going to be absorbance versus time. So now, it will tell me what wavelength do you want to use. And I'll say 632 nanometers, thank you. Wait. 632.0 nanometers. I'm going to click OK now. Do I want to discard the latest run? Yes. Now, what I'm going to do is first of all, I'm expecting a peak on this top graph, which you can't see because my camera is on my top graph, to again be between that yellow and red area in the orange range. This bottom graph here, which you can't really see, is going to be the absorbance versus my wavelength. And I'm going to try to zoom this in as close as possible without dropping either of these computers. Okay. That's probably not going to work, so I'm going to have to reimagine this situation. Just a second. Oh my gosh, I feel ridiculous doing this. Okay, here we go. Whoa, that was the tripod. Okay. Absorbance on my y-axis, measuring absorbance in orange at 632 nanometers. Time is on my x-axis. What I'm going to do is I am going to elect to get my data points. Just a second. Oh boy. Oh boy. There we go. Okay. So I am first going to get my water and my bleach into a cuvette. Cuvette, pipette, one milliliter of water. I'm going to get rid of that pipette tip because I'm done with it. Uh-oh, dancing. It's garbage. Next up is my bleach solution. And the way that I like to mix solutions in a cuvette is, and I hope you guys can see, I like to pipette them up and down a couple of times to make it as homogeneous a solution as possible. Okay, so now this right here is basically a 50% bleach solution because it's 1 part bleach, 1 part water. Now, what I'm going to do on my computer is I am going to go over here and press play. That's going to start measuring, recording data for a good window of time. I'm adding my FD&C, flipped. Oh boy, oh boy. In just a second, I will show you the data. There's my, oh wait. I didn't tell it how long to record the data, so I think it defaults to recording for the rest of time. So I went ahead and I stopped it. And I think that will illustrate what I want to emphasize. What you can see here is our absorbance is our orange line. And so you can imagine that that first point when it shoots up, that's probably when the cuvette was entering the spectrophotometer. Would everyone agree with that? Because it's probably the highest. Now, you could make the argument that, well, maybe it was a little bit higher earlier. And I would concede that argument. But that's the time from when I inverted it to when I put it in the spectrophotometer. And like in an emergency situation, you don't want to freak out because then people get hurt. My question for you is, did anyone get hurt during this? Nope, because I kept a calm, cool head about myself and just said, all right, I'm going to put the cuvette into the spectrophotometer and boom. So you see that the absorbance has a pretty steady decline. Does everyone agree with that? Fantastic. Okay, so that is kind of our midpoint. And at the next point, what I'm going to do is I'm going to take my cuvette with that reaction mixture. And heck, when you look at that, is that even remotely blue? No, not at all. So I'm not just joking and saying, believe me, believe me. Instead, you can see with your own eyes that it's not blue or that it looks different. Okay, so now this trial, what I'm going to do is I'm going to do the 0.5 milliliters of bleach. Half a milliliter of bleach, okay? Bleach solution. New cuvette, so fresh and so clean, it's ready to go. Getting rid of this pipette tip so that I can get another one. And what I'm going to do is I'm going to adjust my pipettement up to 750 milliliters. And the reason that I'm going to do that is because if you take 1.5 milliliters and divide it by 2, it's 750 or 750 microliters. And anytime that you pipette something, there's going to be a little bit of an error. But what I want to do is I want to limit my frequency of errors. So this allows me to only pipette 2 times. So 750. Cuvette. $7.50. Done. Okay. Like I said, pipette up and down. Sound effects are optional, but they do improve the experience. Now, what volume is in there at the moment? 2 milliliters. So now what I need to do is go back to the old pipettement, adjust it to 1 milliliter. Wake up, computer. Wake my computer back up. And when I wake my computer back up, I'm going to go ahead and press buttons to, all right, to record. And erase and continue, so I don't care about that old data. Oh boy. I'm going to take pipettement, 1 milliliter, transfer 1 milliliter into my cuvette. Whoop, whoop. Oh no, my glove broke. But I can take care of that by getting a new glove. And this is a perfect time to get a new glove and check that your gloves are not broken, because the great thing is my experiment's going, so technically I'm working. So, you know, when I was a graduate student, I worked on plants, and so I would be like, oh, I got an experiment going. It's a plant growing experiment. Gotta just let them grow for like 3 weeks. So, you know, a little vacay for me. Not really. That was just one of the things that I had to do. At any rate, I've let this go for, well, significantly longer. And when I send you guys data, you'll be able to compare these things. But what you can see here, what I want you to be able to see, is that we have that same sort of curve. But one thing that makes it a little bit different is the peak is a little bit taller, and it seems to go on for a little bit longer. But like I said, that will be something in the data analysis. Okay, so this will be our second trial. There we go. Now I'm going to go ahead and get the old stopperoo. So now I'm ready for my third trial. My third trial, I'm going to flip-flop my bleach and my water. So last time I did, what was it, half a mil of bleach? And I did 750 microliters 2 times of water. So I'm going to do now 1.5 mils of bleach and 500 microliters of water. So adjust my pipettement to get 750. Hold cuvette out. $750 in bleach. 750 more of bleach. Get rid of that pipette tip. $500 microliters of water. then 1 milliliter of my dye. Before I do that though, I'm going back to my computer. I'm gonna press record so that it starts shooting light at my sample or through the spectrophotometer. Sorry, the spec. So now you know, you're in the know, it's hip, it's cool. Booyah! All right. Peak is going up, it stopped. Now it's going down. Boy, boy, oh boy, oh boy. It went down. Would anyone be able to say, not being able to see, but kind of imagining that last peak compared to this peak? Is this one going down faster? So think about it this way. Is my FD&C's presence in there, is it disappearing faster? Is that something that you would expect considering we had more bleach? Okay. Just a second. Okay, so I'm gonna go ahead and press stopsies on this. And then the last thing that we're going to do, which I am committing what I consider to be a laboratory cardinal sin, and that is I'm touching my phone with a gloved hand. So now whatever I put onto my gloves is now on my phone, but I blame technology for that. I don't take responsibility for that. Okay, so the last part of this procedure is step number 7. Actually, before I proceed, does anyone have any questions about what we did and why we did it? Okay, so the purpose of doing everything that we did was, 1, we had to figure out which wavelength to use. 2, we had to figure out, well, how can we use as little FD&C as possible and still be able to monitor it easily? Because if you think about it, like, we used that concentration that gave us an absorbance of 1. What if we had used a concentration that gave us an absorbance of 0.3? Do you think that the peaks would have been shaped in the same way? The shape of them. Do you think there would be, when we were doing our experiments in our individual assays, do you think that you would have seen the absorbance go up and then go down? Yeah, I think so. But what you would be seeing is you would see a peak that goes up very, very briefly and then goes down very, very quickly. And so you wouldn't really be able to get a good grasp of any sort of rate. Instead, you'd be like, well, after 1/10 of a second, all of it was gone. So I guess that's something I can use. This, we had a consistent and easy disappearance. Now, if you had an instrument, a spectrophotometer that was very, very sensitive and took, 50 readings a second or something like that, maybe you'd be able to use a lower concentration, but you have a little bit of a limitation for the instrument that we're using. But with that said, the instrument that we were using was basically just fine for what we wanted to do. Okay, so then we did our individual assays where we varied, and by a show of hands or thumbs up emojis, has everyone heard the word assay before? We got thumbs up. Okay, so that, if you haven't heard that word, it's kind of like the word aliquot. It's a word that scientists use that means the exact same as another single word, but scientists prefer to use it. So an aliquot is a small volume. Why can't you just say small volume? Scientists won't allow it. Assay, that's an individual trial, or it's an experimental design. I personally think that scientists like to say assay because if anyone's ever seen Looney Tunes comics or Looney Tunes cartoons, there's a Foghorn Leghorn, the big, is he a chicken? I don't know, but he talks with a very thick drawl, and I have always heard in my mind, anytime someone says the word assay, I hear him saying it. I hear I say, because he would always say, I say, ... Anyway, so I think it's a nice like shout out to Looney Tunes. I could be wrong, but we'll see. So when we were doing our individual trials, we varied the amount of bleach because that's what we were curious about. We were curious about how does the concentration of bleach influence our overall reaction, or our overall reaction rate. Does that make sense? Yeah. Okay. Now, step number 7 reads, design additional kinetics trials that will enable you to determine the order of the reaction with respect to the concentration of the NaOCl using the method of initial rates. Fill in the table below. Think about how you need to vary the initial concentration of the bleach, but keep the FD and C concentration the same for each trial. This can be done if the total volume of solution remains 3.00 milliliters. Do at least 2 more experiments using different initial concentrations of bleach. Remember to start the data recording before adding the dye to the water NaOCl mixture already in the cuvette. Export all data to an Excel spreadsheet for analysis. Okay, so let's think about this. We've got some parameters. The way that we have our experiments designed is you got 1 mil of the dye. That's fixed. That gives you 2 milliliters to play around with. Okay. We started with 1 milliliter of bleach, half a milliliter of bleach, and then 1.5 milliliters of bleach, or vice versa. What we did not do was we did not alter. Let me get a glovey glove on. We did nothing to alter this bleach solution. Now, with that information, does anyone have any thoughts on what we could do for another trial? And if you want to type it in, what I'd like is someone to type into the chat the volume of dye, the volume of water, and then the volume of bleach. So, or actually no, thumbs up emoji to raise your hand. Or you could use the raise hand emoji. Anyone have any thoughts of what you could do? So we've got some variables that we don't want to mess with, but this is really getting at the question that's basically being asked is how could you vary the bleach concentration? So one thing that you could do is you had a trial that was 1.5 milliliters of bleach, 1 milliliter of bleach, and half a milliliter of bleach. One option is we could just put 2 milliliters of bleach in. Does everyone agree with that? Because our total volume would then be, 2 milliliters of bleach and 0 water. And you can do that because, well, the FD&C is water-based and the bleach is water-based. So by removing water from a trial, you're not necessarily presenting a huge problem. Does that make sense? So we could go with a 4th trial where we just up the bleach concentration, but that's not really altering our initial concentration. Our initial concentration is the concentration of this solution. So what could we do? What I'm going to do is, I'll be right back. I'm going to take a lap, and you guys think about it for a second, but think fast because I'm on borrowed iPhone time, battery time. I'll be right back. I'm back. Just a second. Does anyone have any thoughts? Remember, it's our initial, let's do. It's our initial bleach solution, or it's our initial bleach concentration that presents the problem, or presents the thing that we could vary. So I would like to propose that we do a trial in which we make a new bleach solution. Show of thumbs up for, I think that's a pretty good idea. Excellent, excellent, excellent. Okay, so what I'm going to do for this is I just want to cut my initial bleach concentration in half. And so what I'm going to do is use my deionized water test tube. And I'm going to take 1 milliliter from there. And I'm going to put it into this test tube. Then I'm going to get a new pipette tip. And I'm going to take 1 milliliter of this bleach solution. And I'm going to add it to this. So now, let's think about what our concentration of bleach, our initial concentration of bleach probably was. So this bleach solution, from a percentage standpoint, has a concentration of about 7.5%. What do you think, and you can type it in the chat, what do you think the concentration of this bleach solution is? If this is a 1-to-1 ratio, our first solution was 7.5%. What percentage solution is this? We started with 7.5 and then we made a dilution. Angela says 3.75. Victoria says 3.75. Here's the tricky part about it. That was actually water. The reason that I was just playing a joke. I made the second most important mistake in a lab, and I didn't label these. And so you look at this and you look at that, and it's like, oh, well, which one's bleach? Okay, I'm sorry. Joking time's over. Yes, 3.75%. You're exactly right. Thank you all very much for participating in that. And I know now I probably look like a jerk because I was like, hey, engage, and you guys engage, and I was like, gotcha, I got a joke. So I apologize for bullying everyone. Okay. Now, what we're going to do is let's think. If this is 3.75% bleach, this was 7.5% bleach, what do you think that this solution will do to the rate of our reaction compared to the 7.5% bleach? Do you think our reaction rate is going to go up or down? Thumbs up for up, thumbs down for reaction rate goes down. I got thumbs down. Yes, 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 I see lots of thumbs down. Yes! Because, well, as we saw, when we increased our bleach concentration in our reactant, or in our reaction rate went up. But now, since we're starting with something that's half the dilution, well, it's going to slow down a whole lot. Make sense? Okay, now let's see this in action. All right, cuvette. Got it. I'm just going to do the 1 mil, 1 mil, 1 mil, because I think that's going to illustrate the point. Does that sound good for everyone else? Great. Okay, I need 1 mil of water. Then I got 1 ml of my bleach solution. Now what I'm going to do, I'm going to press record so that I can start collecting data. Now, I'm going to add my FD&C. This data is looking good, y'all. I think it might be bold and maybe reckless to say that we're the best group of scientists ever, but got to be in the top 3. Yep. Yep. Okay. We can give a few more seconds. But while we're waiting, does show of hands for everyone who likes Sonic drinks? Show of thumbs up. I'm sorry. Okay. Does anyone have a favorite Sonic drink? Good, good. I don't want to know what it is. I just want to know that you have one. I'm partial to the R44 CVDP. If you can decode that, give yourself a pat on the back. That's a Route 44 Cherry Vanilla Dr. Pepper. When I was a kid, I was a cherry limeade fan, but you know, when you become an adult, you leave childish things behind, and that's what I did with the cherry vanilla, or the whatever I just said. Okay. I'm happy that we designed the experiment that we just designed and that we did it, because I think it really looks pretty cool. One of the things that, if you remember from those previous graphs, we saw a peak and then either a pretty sharp drop down or a gradual, like I'm not sure if anyone's a skier. I'm not, but I know like two terms, a bunny slope. We saw either a bunny slope or a called like a double diamond or something, a black diamond or something. Again, not a skier. So the bunny slope is, whereas the black diamond's like, yeah, straight back down to the ground. What we're seeing, and think about those two, that black diamond, that was the sharp that we saw our FD&C disappear super fast. The bunny hill or bunny slope is, it's still there, it's still there, it's still there, oh, it's gone. Okay. If anyone's a hockey fan, the gloves are off. That means I'm ready to fight. I'm not ready to fight, but now this is an intense moment. Okay, we saw a peak. And let's look, can everyone see where 0 is on our y-axis? My question for y'all is, did our absorbance ever hit 0? No, it didn't. In all of our previous trials, it hit 0. We got rid of all of the FD&C. In this case, we're only getting rid of about half of it, or maybe I'd say about 2/3 or so, half to 2/3 we're getting rid of, but there's still some FD&C. Now I'd like to show you, oh man, the glove, I gotta put a glove back on. You guys are gonna look at the ceiling, or you're gonna look at the floor for a second. Okay, I've got a gloved hand and an ungloved hand. This right here is a previous trial. All our FD&C is gone. Now, I haven't looked at this and I haven't done this trial yet, but do you think, show of thumbs up, a show of thumb up if you think that you will be able to detect, just by looking at it, that it's kind of blue, the solution? Okay, I got 1 vote. I'm thinking yes. I'm thinking it might be a little bit blue. I think there will be like the remnants of blueness. Okay, no, not at all. But what I want you to appreciate about that failed demonstration there is that this instrument right here, our old friend, the UV Vis Spec, is super sensitive. Even when there's only 5 of that molecule out of 100,000 molecules, it can detect it. I cannot, despite my perfect 20/20 vision. I can't. So that shows, I want that to show you that this is a very powerful and useful instrument because it can detect a very, very small amount of that substance still in there. Does that make sense? Okay. Now, this is all the demo. This is all of the experiment. What I'm going to do is I'm going to provide y'all with some data. I'm also going to provide y'all with a video dissecting that data. And so I'm hoping to get that video posted either today or tomorrow, where I dissect some data, some experimental data, and then you guys are going to do the same thing as a part of your report. At the end of the day, all that we care about with this is what type of graph we produce. And that type of graph is going to tell us, is it 0th, 1st, or 2nd order with respect to our sodium hypochlorite. How's everyone feeling right now? Okay, now my question of questions. If there were $100 on the line, do you think that you could come in and do this experiment and knock it out? Okay. There's going to be $100 on each one of these benches tomorrow. Not really. I don't have $100 cash, and you know the coin shortage and everything. My $100 coins are missing. Just a second.